All right, so we're now recording. We're going to go over a couple quick limit applications, maybe a little bit of continuity as well. This is number 3 in the notes from Limit Apps Day 2. This was not completed in the video, but I thought it would be a nice additional example to work through just to get a little bit more practice with derivatives. So the limit definition of a derivative is it's the limit as h goes to 0 of f of x plus h minus f of x over h. And this whole thing I mentioned in the video should look familiar from the beginning of the year. This is called the difference quotient. So it's something that we did use at the beginning of the year, but we didn't have a limit out in front. Taking the limit as h goes to 0 is finding what's called the derivative for the function f of x. And again, what that represents is it's the slope of the tangent line to any point on the curve. The function that you're given in number 3 is 2x squared minus 3x. And we eventually want to find the equation of the tangent line at the point 1, negative 1. So to get started, I'm going to take the limit as h goes to 0 of this first piece, f of x plus h, would be plugging in x plus h for both of those x values. So it's going to be 2 times x plus h squared minus 3 times x plus h. And then from that, we're going to subtract the whole function f of x, which is 2x squared minus 3x. So you can put that whole thing in parentheses because you're going to have to distribute that negative sign. And then this would be all over h here. Okay. From here, you have to expand out the top. So you're going to simplify that entire expression. And then hopefully everything that's left over has an h in it. Okay. So when I do the x plus h squared step, I'm just going to write off to the side what that is. You would either have to FOIL that, multiply it by itself, or do some box method. But that is x squared plus 2xh plus h squared is what this is. Okay. So knowing that that's what it equals, why did I write that off to the side? Because I want to distribute a 2 into all of that. And make sure you follow PEMDAS, right? You do have to square it first before you distribute the 2. So if I distribute a 2 to all of that, you are going to get 2x squared plus 4xh plus 2h squared. So now that I've done that step, I'm going to distribute the negative 3 to get minus 3x minus 3h. And distribute the negative here to get negative 2x squared plus 3x. And that's all over h. For my muted guests today, again, if you have anything that you have questions about as we're working through this, chime right in and let me know. All right, now you should be able to cancel some things. So we got 2x squared and negative 2x squared, which cancel. You're going to get negative 3x and positive 3x to cancel. So we get the limit as h goes to 0. Now, what I said earlier is that everything left over should have h in it, and it appears that that's true of these 3 terms. So we're going to factor out h as a GCF to get 4x plus now this would become 2h, and at the end, minus 3 all over h. The reason why it's critical to be able to factor that h out from the remaining terms is because you have to get rid of this h on the bottom. Because right now, if I plug in 0 for my h's, you're going to get 0 over 0, which is no good in terms of evaluating limits. But now that those h's cancel top to bottom, we're going to take the limit as h goes to 0 of 4x plus 2h minus 3. And all that we really do to evaluate this limit is you're going to take 0 and plug it in for h specifically. So this middle term actually just goes right to 0. When I evaluate that limit, we get 4x minus 3. So using proper derivative notation, the derivative of f of x, which would be f prime of x, is 4x minus 3. Now, the nice thing about having f prime of x, as compared to what we do in day 1, where we only plug in a point that's close by, is that now you have a function that would find the slope at any given value of x. Now, I've given you the point 1, negative 1 at the start, so we're going to use that coordinate. But if you wanted to find the slope anywhere else, we have a function that models that, and that's what this is right here. So given that we want to be tangent at the point 1, negative 1, whatever the x value is of your point that you're given, plug that into the derivative. So 4 times 1 is 4, and then minus 3 is 1. That 1 represents the slope of the tangent line at x equals 1. And you certainly don't have to write that statement, but for those of you that have a tough time understanding what does that even represent, that is the slope of the line that is tangent to this graph at the point 1, -1. So using this slope and the point 1, -1, you're going to write the equation y plus 1 equals my slope of 1 times x minus 1. So we're using point slope form, just like we saw in Limit Apps Day 1, to be able to write that equation. So I'm going to stop here for a second and then see if you have any questions for my people who are here in today's meet. Anything about this example? All right, I don't hear anyone unmuting or typing into the chat there. So what I'll tell you is that the only thing that was added on for tomorrow's lesson, just while we're kind of sitting here talking about some derivatives, there's really only one new thing tomorrow. So if you can understand this concept that we're looking at right here, I think you'll definitely be able to catch on quickly to tomorrow. There's going to be a part of tomorrow's lesson that says, are there any points where the graph has a horizontal tangent line? So if you think about a horizontal line, I'm hoping you're thinking that the slope of the line is 0. So what that means is you're going to take the derivative, which represents the slope of the tangent line, and you're going to set that equal to 0. So the derivative equation up here was 4x minus 3. If you solve that real quick by adding the 3 over and dividing by 4, you get x equals 3/4. And what that means is if you go to the graph of your parabola that we're talking about here, at x equals 3/4, now I'm guessing this is a parabola that must dip below the, something like this, okay. At x equals 3/4, you're going to get a line that's horizontally tangent to the graph, having that slope of 0. Why is that kind of a good piece of information to know? A horizontal tangent to a quadratic function is where it exhibits its min value. Or I guess if it was upside down parabola, it's where it would have its max value. So the reason why we care about horizontal tangents is specifically for parabolas and other polynomial functions. It can help you quickly identify where min and max values are. So this will be the only new thing that gets added on to tomorrow's lesson. The other thing you're going to do with x equals 3/4 is you're going to plug it back into the function to get the y value, which in this case is not going to be a nice y value. Do 2 times 3/4 squared, whatever that y value comes out to be. You would write it as the point 3/4, comma. I'm going to put a question mark for now without a calculator next to me. Okay. So when you'll see a couple more examples like that tomorrow, and then you'll let me know if you have any questions about it. All right. All right. So that's it for this first thing that I wanted to do, just kind of a recap of what today's lesson was all about, which is finding a derivative using this limit definition. Before I talk about continuity, which I think is also an area where students might have some confusion here and there, do you guys who are here want to chime in with anything, questions about this example or otherwise? Okay, not seeing any questions there. So I think it will be nice to maybe just do a quick review of what I was saying a second ago with the limit definition of what makes something continuous. We can look at a graph and see pretty easily whether or not something's continuous at a given value of x. It's just, can I draw the graph without picking up my pen or pencil? But there's definitely a little bit more of a formal way of defining continuity in math, and it has something to do with limits. So I want to kind of separate the types of discontinuities and the reasons why something may or may not be discontinuous at those values. So there are 3 types, and then there are 3 reasons why we have discontinuities. So the types are removable. Hey, Sean, thanks for joining us today.
Hey.
How we doing?
Pretty good.
Pretty good. I like it. All right. It's beautiful weather, but I appreciate you jumping in to join us for a little bit. Sean, we actually just did we did a little bit with derivatives from what today's post was on day 2 of limit applications. And now I'm just going over a little bit of a review of the continuity lesson from earlier this week. So
all right.
After I'm done with this, if you have any specific questions, feel free to chime in with those.
Okay.
Okay. All right. The other types, other than removables, we have an infinite discontinuity, which is pretty much when you have an asymptote. And the last one, it seems odd that it's such an informal name of jump, but jump is an official type of discontinuity. And you're going to see that primarily in piecewise functions. Okay. If something, and when I say types, by the way, I should really say that this is types of discontinuity. Okay. If it doesn't have any of these 3 things, an asymptote, a hole, it's not a piecewise jump, then the function's continuous. But types of discontinuities are these 3 names. So on the test, if I ask you what type is it, one of these 3. And be a little bit cautious about that. Don't say asymptote is the reason. I really want to see infinite as the name. What's in parentheses is just kind of a clue on the graph as to what to look for, but you wouldn't say the type is piecewise. You would say the type is something like jump. What are the reasons why something might be discontinuous at, let's say, I think I used in the notes, at some x value c? Well, one reason might be that f of c doesn't have a value. Okay, so on the graph at x equals c, there's no y value at all. That's a good reason that we're discontinuous there. Another reason why we might be discontinuous at a value x equals c is if the limit does not exist. That happens a lot in piecewise functions if there's that jump, right? If you're coming in from the left side of c and the right side of c and you're approaching different things, if the limit does not exist, you can't be continuous at x equals c. And the third reason, which I don't think is as common as 1 and 2, but it certainly applies, is if the limit as x approaches c does not equal f of c. So if both of these things exist, but they're not the same value, then that's a reason we'd be discontinuous as well. So just as kind of a quick example of what we're talking about there, if we have something like this function here, let's make it something like this. Now, this looks like piecewise, and I don't want you to think that piecewise is automatically jump specifically, but if I gave you this function right here, this one has a removable discontinuity at x equals -1, which is why I've defined it in this way. If you were to factor that top, you would get this. The x plus 1's to cancel. So you're going to graph the line x minus 1 everywhere except where x equals -1. Because x equals -1 would make that 0 over 0 case. Okay. So if I look at the graph of what this looks like real quick, at x equals -1, if I plug in -1 for this function, -1 plus 1 would actually be, or -1 minus 1, sorry, would be -2. There's going to be a hole in the graph there. Okay. But that's what that first part would look like at the top. The second part, when x equals -1, it says graph a y value of -4. So there's going to be that closed circle right below it. So based on this graph and based on the original definition of f of x, what type of discontinuity do we have? Well, based on the fact that we factored and removed this factor of x plus 1, we're going to say it's a removable discontinuity. And then if I ask you, what's the reason why we're discontinuous? Let's look at our 3 reasons. Does f of c exist? Yeah, I mean, f of -1 has a value. F of -1 is going to be -4. Okay, by the way, it's discontinuous at x equals -1. Okay. So f of -1 exists. Does the limit exist as x approaches -1? Yeah, as I approach -1 from the left and right, I'm getting closer and closer and closer to the same y value, which is -2. But since the limit and the function value don't match, the reason why we're discontinuous is that the limit as x approaches -1 does not equal f of -1. Okay, this side would be the y value of -2, whereas this side is equal to -4. You don't have to write those bracket part underneath. This is a justifiable reason right here all by itself. But here's kind of what the graph might look like to use that last reason that I listed up here. That's, I would say, one of the tougher ones to identify, but the other 2 we see definitely more frequently. If I were to give you the function, let's say f of x equals 1 over x minus 2. If I ask you, is this discontinuous anywhere? Anytime you see a fraction, I'm hoping you're thinking, yeah, it's definitely discontinuous where whatever x value makes the denominator equals 0. So this is discontinuous at x equals 2. But then you have to list a type and a reason that go with that. So maybe you can even think about what the graph looks like. At x equals 2, there's that vertical asymptote. And as soon as I say asymptote, the type is that infinite discontinuity. And the interesting thing about the reason for this one is you can use one of 2 things. You can say f of 2 has no value. Or I would even accept, I think this is probably the easiest thing, by the way. The limit does not exist either. Okay. Notice that when I list the type and the reason, I'm trying to make it specific to x equals 2. So don't tell me limit as x goes to c here. Try and say limit as x approaches this discontinuous value of x2. Okay, and include that in your reasoning. Okay, last case is just that jump discontinuity. I'll just show you a picture of what that looks like. Even though it's in the notes from day 5, it's going to be a piecewise function where, basically the limit does not exist. So you might have something, like linear like this, and then maybe you have like a parabola looking thing. Okay, so if I call this x value c, whatever that might be, this is discontinuous at x equals c. The type that we have is a jump. All right, we definitely have to jump from this part of the graph down to this part of the graph. And then the reason why we're discontinuous at c is not because f of c doesn't exist, because f of c does exist. We have that closed circle here. It has a y value. But the limit as x approaches c does not exist. When I approach c from the left and when I approach c from the right, we're heading towards 2 different y values. So that's the official reason why we're not continuous there. Okay, I've kind of blabbed on for a while about continuity there, but it does tend to be one of those areas where students might have questions and maybe tend to make more mistakes than not. So for my participants today, anything that you have questions about as it relates to continuity? Not seeing anything come up there. So for those of you here today, and again, I'll post this video later on. I thought I could switch the camera back. How do I do that? Usually lets me. What I was just going to say quickly is that the last test will be posted probably at the beginning to middle of next week. We're going to have one kind of final review sheet that you'll work on starting Monday. You'll continue working on it Tuesday. We'll probably have another Google Meet Tuesday to meet up, and you can ask some last minute questions for me. And then the final test is kind of a combination of 2 tests we would have taken in class. So you can almost think of it, I guess, as a little bit of a final exam. It might take you longer than what a 40-minute test in class would look like, but work at your own pace. If it takes you an hour to complete, that's fine. If you finish it in 40 minutes, that's clearly okay too. So, questions I can answer for you guys as we wrap things up here. I definitely appreciate you guys coming today. But nothing else real quick before we finish up today?
What lesson number are we supposed to be on? Like completely 100% caught up?
Sean, that's a great question. And I know you're asking that for others who need to hear this.
Yeah.
But to be completely caught up right now, today's post would be Limit Applications Day 2. Limit Applications Day 2 is what's on the definition of the derivative. So if you're completely caught up, you've done some limit applications at this point up through Day 2.
Okay.
Now, Sean, let's pretend like you've already watched Limit Day 2 and you're all caught up. I will tell you that just before today's Google Meet, I posted Limit Applications Day 3, which is the very last video lesson of pre-calc. That's it. So if you want to get ahead and enjoy tomorrow with no math to worry about, you could actually do that. So, but yeah, there was a new lesson each day this week, which I apologize for, but it was the only way to kind of squeeze everything in so that we'll have time to do some good review next week and take our last test. So thanks for asking that question, Sean.
Mm-hmm.
Anything else from the group? Well, I certainly don't want to hold anyone back then from enjoying the beautiful weather today. So go ahead and enjoy. Thank you so much for coming. And I'll post this video later in case there's something you want to check back in on, or if somebody asks what happened today, it'll be posted on the website later. All right?
Thank you.
Yes, thanks for coming, guys. Let me hit stop record.
Have a good day.